Okay, so now we're going to talk a little bit about rotational dynamics. Before we do so, I just want to remind you about the relationship between kinematics and dynamics. So in kinematics, what we're trying to do is describe the motion. So the position as a function of time, the velocity as a function of time, the acceleration as a function of time of some object along the x-axis. And so the basic idea is if we know any one of those three, we can determine the other two just by either integration or differentiation. So fortunately, we do know one of those three. We know what causes changes in motion, changes in velocity. We know what causes accelerations, and that's forces. So if we know the net force acting on an object, then we know the acceleration of the object. Then we integrate to determine the velocity, and then integrate again to determine the position as a function of time, given the initial conditions. So given the initial position and the initial velocity and the force as a function of time, the net force, we can then solve the motion completely. Okay, we talked about this for linear or translational motion. So here linear, say, just along the x-axis. So the question that we have now is, what is the rotational analog of this whole basic structure of Newtonian mechanics? Okay, so instead of a position along the x-axis, for rotational motion, we have the angular position of the rigid body, theta. And instead of the velocity along the x-axis, we have the angular velocity, radians per second, that this object is rotating with. And then instead of acceleration along the x-axis, we have an angular acceleration, the rate at which the angular velocity is changing. So that's alpha. So the question, and we talked about the kinematical relationships between these three descriptions of the motion. So now what we really need is, well, what causes angular acceleration alpha? So what we're looking for is the rotational or the angular analog of a force. Okay, and that analog is called torque. So it's given the Greek letter tau, T-A-U, tau, and it is torque. And torque is a kind of twisting force. Okay, so rather than a force along the x-axis causing acceleration, what we're wondering about is what kind of a force is required to cause an object to rotate faster and faster and faster, to have an angular acceleration alpha. Well, that's some kind of twisting force, so called a torque. And that's what we're trying to figure out now. What is this thing called torque? So what we're going to do is we're going to start with, what we know. So in linear motion, we know that if we have a mass m, and we apply a force in the x direction, along the x-axis, this is the x-axis, we know that when we apply that force, it's going to cause an acceleration of that mass along the x-axis in the x direction. And that acceleration is the force divided by the inertial mass, the resistance of this object to changes in its motion. Okay, so that's easy. Okay, so now we're going to take this and we're going to expand this to understand what torque is. Okay, so for rotational motion, what we have is we're going to start with the same mass, m. Okay, and what we're going to do is instead of an object, a mass m moving along the x-axis, what we want is a rigid body that's going to rotate. And so what we do is we take this mass and we construct from it the simplest possible elemental rigid body. And that is, we take a pivot point over here and we attach the pivot point to the center of mass here with a massless rigid rod, okay, of length L. And so when we apply a force to the mass in this direction, it won't go along the x-axis, but what it will do is it will rotate around like this. And so we apply a force and it'll undergo an angular acceleration, it'll pick up angular velocity, and sometime later it'll be over here. Okay, and then it'll be moving around and around in a circle like this. And so basically what we have, this is the model of it here. This red ball is this mass here. And we apply force in the x direction, we cause this ball to accelerate in the x direction. But now we've attached a massless rigid rod with a pivot point here, and the axis of rotation is perpendicular to the board here. And what we're doing is we're going to apply force at the end here, and it's going to cause this very, very simple rigid body to undergo angular acceleration, to start spinning faster and faster and faster around this axis. Okay? So why do we think of this mass connected on the end of a massless rigid rod as an elemental rigid body? Well, the answer is that any rigid body can be constructed out of a whole bunch of these guys. Okay, so if you take any rigid body, so any three-dimensional body like this, volume, and we're going to have this body rotate about some axis, say this axis over here. And so we're asking what sort of twisting force, do we need to apply to get this object spinning faster and faster and faster around that axis. And you can take any three-dimensional rigid body like this and break it up into a whole bunch of little chunks of mass. So these little chunks of mass are like this ball here. Okay, so this is, say, mass M1 sits over here, and it is a perpendicular distance L1 from the axis of rotation. And then take another chunk of mass, say over here. This is mass M2, and this mass M2 is located a perpendicular distance L2 away from this axis of rotation. Now, it doesn't look perpendicular. I'm drawing it in a three-dimensional perspective sense. This mass is coming out of the board like this. Okay, and maybe we have a mass M3 over here, and it's connected with a massless rigid rod, effectively, to the axis of rotation of length L3. Okay, so we can always take any three-dimensional object and decompose it into a whole bunch of these elemental rigid bodies. So this is a very common rigid body to think about. If we can figure out the twisting force required to cause angular acceleration of this very simple rigid body, we can do the same for any rigid body. That's the plan. Okay, so what we're going to do is we're going to apply a force, the same force. Okay, but instead of calling it force in the x direction, we're going to call it force in the tangential direction, because that force in the tangential direction will be applied in the direction tangential to the circle that this mass moves around on as the body's rotating faster and faster, this elemental rigid body. So we'll take that tangential force to be the same strength as Fx here. And so then that, that tangential force is going to cause a tangential acceleration. Okay, so remember, when a rigid body rotates faster and faster and faster, any point on that rigid body is undergoing some tangential acceleration, meters per second squared tangential acceleration. And that tangential acceleration is, because the mass is the same, the magnitude of the force is the same, obviously it's going to be the same as AX. Okay, and we know that AX is Fx divided by the mass, and Fx is the same as the tangential force. Okay, so we've got that so far. But we also know what we're really interested in is the angular acceleration, not the tangential acceleration. But we know that the tangential acceleration and the angular acceleration are just related by the radial distance, or in this case the radial distance is L. Okay, so the tangential acceleration at this point is equal to the length L, okay, the distance from the axis of rotation, times the angular acceleration. This is in radians per second times meters gives you meters per second. Okay, so going back to this side, just sort of the kinematics here. When this mass is moving around, is accelerating like this, there at some point you will reach some angular position theta, and that theta will be changing with time. So d theta dt, the rate at which that's changing is the angular velocity. We're not interested in the angular velocity, we're interested in the time rate of change of the angular velocity, which is the angular acceleration alpha. So we're talking about rotation about this axis, the angular acceleration, okay, about that axis. So what we have is a relationship between Ft and alpha. So let's write that down first. That's an intermediate result that we're going to expand upon. So this says Ft is equal to m times L times alpha. That's an important first result. Now, this is already starting to look a little bit like, F equals ma. But instead of m here, we have m times L. Okay? But we're not quite done. In the end, we're going to have to multiply this whole equation through by L. Okay? And so we'll try to figure out why here. Okay, so one way to think about this, just sort of intuitively, it's important that you understand stuff intuitively before we, go through all the details of the math. But it's also important that you understand the math. Okay, so let's make a little bit of room here. All right, very good. Okay, so the intuitive idea is something like this. So suppose that you have a heavy door that you're trying to push open, and we're going to view the door from the top down. So on the left-hand side is a hinge, and then comes the heavy door. And the idea is we're going to push on this door to try to cause this door to undergo angular acceleration, because we're trying to open this door, right? And so when you open a door, it starts with 0 angular velocity, and then you push on the door, and then the angular velocity of the door increases. Okay, and so there's some angular acceleration. So we want to exert a force on that door to cause angular acceleration. Okay, and so so what you do know intuitively is that to open that door, it's a lot easier to open a heavy door by pushing on the end that's furthest from the hinge. You need to exert only a relatively small force at the end furthest from the hinge to swing that door open. And it's kind of stupid to exert a force very close to the hinge, because you know that you're going to have to push a lot harder. Okay? So what starts to come into our mind here is to produce angular acceleration, the point of application of the force matters. Okay, to produce the same angular acceleration by pushing on the end, only a small force is required. But to produce that same angular acceleration closer to the hinge, a large force is required. So it's not just the force that matters, but the point of application of the force. How far away from the hinge or the axis of rotation should you be pushing? Or how does that force depend upon how far you are away from the axis of rotation? So the way we're going to do this sort of formally here is, I might need a little bit more room over here. So let me take this away here. And let us translate this diagram into this diagram over here. Okay, so what we've got is, I'll just repeat the diagram over there. What we've got is a pivot point over here. We have a massless rigid rod that we can push on at any point, and we have a point mass M attached to the end of that rod. Okay, and in this situation over here, what we did is we applied a force that we called F tangential at the very end of that rigid rod of length L. Okay, and now we're going to ask the question, well, what force applied somewhere in the middle over here, so some distance r, from the axis of rotation here, force here, what force applied some distance r away from the axis of rotation instead of a distance L away from the axis of rotation is going to have the same effect as the force Ft applied at distance L away? Well, we know just intuitively that that force is going to have to be larger. So we'll call that force, we'll give it a different name. Instead of capital Ft, I don't know, let's call it little ft. Okay, that doesn't really look like a little f. Okay, so let's put a little ft in there, just to distinguish it. It's still a tangential force. It's still tangential to a circle. So this point, as this object, as this elemental rigid body starts to undergo angular acceleration faster and faster and faster, it will rotate through some angle. So suppose it has, after a second or whatever, it has rotated through this angle over here. And we'll call this angle d theta. Okay, so it's a very small angle theta that we've rotated it through. Okay, and so when this rigid body rotates through an angle d theta, then this point will move through an arc length equal to, let's call that ds. Okay, and at the same time, this point will have moved through a smaller arc, an arc of shorter length, which we will call, let's say, ds prime. Okay, so now the question is, what force, little ft, needs to be applied at a distance r to have the same effect as a force big Ft applied at distance L? So now you might wonder, well, what do you mean same effect? Well, what we mean is causing the same amount of angular acceleration. But an equivalent way to think about that is how much energy this force little ft is moving through a displacement ds prime. And so force times distance is energy transferred to the door. Okay. Alternatively, we have a force capital Ft acting through a larger displacement ds, and so force times distance will be the energy transferred. So if the same amount of energy is transferred to the door by the force Ft acting over displacement ds as force little ft acting over displacement ds prime, then you're going to produce the same angular acceleration. You've transferred the same energy to the door at the end of the day. Okay, so let's look at that. So the work done is the energy transferred. In this case, it's kinetic energy. We have this massive object now in motion. There's some kinetic energy for that mass. Okay, so the energy transferred is the force times the displacement. They're just parallel to each other, so it's simple. So the energy transferred to the door by force Ft acting through a displacement ds is Ft ds. Now, the crucial thing is this. So this is Ft, and then the question is, what is ds? What is that little arc length? Well, that little arc length is the angle d theta times the radial distance, L. So this is L d theta. And we want to equate that. That's the amount of energy this guy, force Ft acting through displacement ds, transfers to the door. We want to equate that to the amount of energy that force little ft acting over a displacement ds prime transfers to the door. Okay, and so, or this rigid body. And so this is little ft, and then ds prime, this little arc length, is the angle d theta times that radial distance r. So it's r times d theta. So we want to equate this to this. Okay, and so what this tells us is that L times big Ft is r times little ft. So that's the important result. So little r times little ft, or r times little ft, is equal to L times ft. So what you see is that LFT, suppose we had, a rigid body of some length L here, and we apply a given force. Let's suppose that this is known. So this force and this force Ft applied at a distance L from the axis of rotation will cause a certain angular acceleration, or will transfer a certain amount of energy to the door or to the rigid body when it goes through some angle d theta. And what we notice is that in order for Ft, little ft, to have the same effect, then we need r times Ft to equal that. So if we make r smaller, then little ft will have to be larger. So if you're closer, little ft is larger. If you're not as close, little ft is smaller. And so you see how it goes like this. It gets harder and harder to open that door. You have to push harder and harder to have the same effect, to cause the same angular acceleration of that door or of that rigid body. So as r decreases, little ft has to increase. So what counts here is not the force itself. What counts is the force times the radial distance times the distance away from the axis of rotation. It's the product of the two that matters as far as angular acceleration is concerned. And that product of the perpendicular force, or of the distance times the perpendicular force, that thing is called torque. That's the twisting force. Okay? So great. So then, so this torque, tau, is equal to r times the perpendicular or the tangential force. That's the torque. And that's equal to L times capital Ft. Well, here's Ft. Now, like I said before, we want to multiply the whole equation by L. So we end up with L times capital Ft is ml squared. That's important, that square, times alpha. Okay? And so let's just, and this is the end result. Now let me just sort of generalize this. I'll just write this in a more general notation. So the rotational analog of F equals ma, or Fx equals max, the rotational analog of that is, instead of a force along the x-axis, we have a twisting force. So this is clearly a twisting force. So it's the same as, grabbing this thing and twisting it like this, applying a force some distance away from the axis of rotation. is effectively the same as twisting this rigid body and making it accelerate. Spin faster and faster and faster, say counterclockwise. So this is the torque this is the twisting force, or the torque. Okay, and that's equal to, so ml squared in this case is something called I, the moment of inertia. And this is the moment of inertia of the simplest possible elemental rigid body. Okay, so in general, if you have a general rigid body like this, as we said before, that rigid body is composed of a whole bunch of little masses perpendicular distances away from the axis of rotation, and then you just add ml squared, so this m times this l squared plus this m times this l squared plus this m times this l squared, and you sum over the whole body, and then you'll get the moment of inertia, and that's the resistance of that rigid body to changes in its angular motion. So changes in omega, so alpha, angular acceleration. So this thing is called the moment of inertia. And we'll talk much more about this. So moment of inertia. So it's some kind of an angular inertia. This is the inertia for linear translation, for the resistance that the object presents to changes in its motion under linear forces. This is the resistance that an object, a rigid body, presents to changes in its motion, angular motion, okay, times alpha. Okay, so we have achieved the rotational analog of this equation in linear or translational motion. Okay. Yeah, so now what we're going to do is we're going to talk a little bit about moment of inertia and more about torques. Okay, so we're going to analyze this whole torque thing in a little bit more detail. All right?